So today we'll read about nucleation and growth. So when we're talking about the phase diagrams and the different phases will form, there will be structural changes. That means the microstructure of the material will be changed. The microstructure of the material change or the structural changes will be taken place by two ways. That is called as, one is called as the nucleation and other is called as the growth. One is nucleation and other is growth. So we'll study about this, what is the nucleation and what is the growth. The factors or the variables which affect the structural changes or the phase transformation are, as we have already discussed these things, that is your that is the temperature, pressure and composition. The three variables which is responsible for the phase transformation as well as the diffusion. Okay, along with these three, okay, just wait. Someone is in waiting room. My waiting room is activated, so I want to disable waiting room. So the two factors there are generally along with the diffusion, like the temperature, pressure and composition, the diffusion also plays an important role for the phase transformation. So in diffusion, the two factors that affect transformation rate, when we are talking about the transformations, that means the phase transformation, the how the phase transformation will take place. The phase transformation will take place like your diffusion control rearrangement of atoms because of compositional and crystal structural differences. One thing is that first thing is that the diffusion control rearrangement of atoms. Diffusion control rearrangement of atoms. So that means there is a rearrangement of atoms. That means we can say sometimes the crystal structures will be rearranged. The structures of the materials will be rearranged due to the diffusion. And that may be due to the crystal structure differences, due to the crystal structural differences, or maybe due to the diffusion control rearrangement. So the second factor is difficulty encountered in nucleating small particles. There are maybe some very small particles are there in the crystal structures. So there are difficulty may be encountered in nucleating that small particles. So by changes in surface energy associated with the interface, that will be depends largely on the surface energy of the material. So just nucleated particle has to that nucleated particle has to overcome the positive energy associated with new interface from to survive and growth further. Okay, it is does by reaching a critical size. So nucleation, and there is the term the nucleation and the growth. The term nucleation means when the new phase or the new structural changes will be started to forming. And the growth is that after the formation of after the nucleation of the structures, that will be grow. Due to that is maybe due to that is largely due to the diffusion processes. So there is the large amount of positive energy associated with the new interface. So that means we have the new formation of the structural changes or the phase transfer. So is it audible? Am I audible? Okay. So the network issues, that's why some problems are there. So we'll continue here. So the main factor is we have to overcome the positive energy that is associated with the new interfaces. So if you see the nucleation, so there is generally two types of nucleation. One is called a homogeneous nucleation and other is called the heterogeneous nucleation. The homogeneous nucleation, or we can say that is kinetics. homogeneous nucleation, or we can say that is the kinetics. What does it mean that homogeneous nucleation? What do you mean by that term, the homogeneous nucleation? The homogeneous nucleation refers to the nucleation occurs within parent phase. Nucleation occurs within the parent phase. That means the phase at the initial level of any crystal structure will be, if that nucleation occurs at that level, that is called homogeneous nucleation at the parent level, parent phases. So all sites are equal probability for nucleation. That means here what happens, all the sites, that means the region which is prone to be crystal phase transformation or structural changes, that all are equally probability for the nucleations. So but it requires considerable undercooling. So how can we admit this? How can you consider this? It requires considerable undercooling. Undercooling means cooling a material below the equilibrium temperature for a given transformation without the transformation occurring. So what is that undercooling? The undercooling meaning is given here. The cooling a material below the equilibrium temperature for a given transformation without the transformation occurring. Undercooling means at that the temperature at which we are not, the cooling process cannot be, the phase transformation cannot be done without any phase transformation. It will be done at the on. Really late. So let's see. So there is a free energy change associated with the formation of new particles. The new particles will have the free energy change. That free energy change is equals to that formula. Del F is equal to 4 by 3 pi r cube del G plus 4 pi r square. That is your gamma. So where r, as you know, r is the radius of the particle. Del G the gives free energy change per unit volume, and gamma is the surface energy of the interface. So see, this is the free energy which I am talking about, the energy level of the particles, of the new particles. That is the free energy level of the particle, that will be written as del F is equal to 4 by 3 pi r cube del G plus 4 pi r square gamma. R is the, as you know, there is the variables. What are the variables here? This is r, del G and gamma. So r is the radius of the particle, del G the gives free energy change for unit volume, and gamma is the surface energy. This is the free energy change associated with the formation of new particles. This is the formula. This is one of the important formula, how the nucleation will occur, homogeneous nucleation will occur, and what is the energy level of the new particles. This is the homogeneous nucleation. And if you see the critical value of disturbing elements are there. So how we'll go to the homogeneous nucleation processes. So critical value of particle size, the R, which reduces with undercooling, is given by, when we are going for the undercooling processes, in undercooling process, the value of R, or the otherwise you can say that is the critical value of particle size, that will be reduces, and that will be reduces by this formula, R equals to minus of 2 gamma by del G, or R is equal to R equals to 2 gamma Tm by del Hf del T. So where Tm is the freezing temperature in Kelvin, del Hf is the latent heat of fusion, and del T the amount of undercooling which nucleus is formed. Okay, so this is the formula. Controls. Again, 3 people are here. Okay. We'll see here how the critical value of particle size will be reduced by during the undercooling processes or due to the undercooling process. If you're going for the undercooling, then there must be the change in size, or the size of the particle must be reduced. That formula is written as R equals to minus of 2 gamma by del G. As you know, gamma is the free surface energy, del G is the free script energy per unit volume, and this is gamma. Here is the new term is Tm. Tm is the freezing point temperature in Kelvin, and this, remember this things. Tm is the freezing point temperature in Kelvin, and del HF is the latent heat. As you read in the thermodynamics, it is the latent heat of fusion, and del T is the temperature difference. Temperature difference. Which temperature difference? This is the undercooling temperature differences at which the nucleation will occurs. So before we move, this is the curve which is shown against the free energy, the energy of the particle del F against the del F against the equilibrium temperature. As we see with the disturbing. So as you see here, the energy levels, that equilibrium temperature, the free energy, and the critical radius are three factors. Three parameters will be shown in this diagram. See here, the critical radius, where the temperature is lower. This temperature. See this T4 is less than T1. This is T1, T2, T3, T4. Four temperatures are given, and radiuses are R4, R3, R2. R1 is not given here. So R2, R3, R4. Sorry for the interruption. That is due to the network issues. I don't know why today so much of network issues. So if you see, as you said that with the decreasing in temperature, the critical radius of the particle decreases. See, this is the at T2 temperature. This is the critical radius, that is R2. Here at the R3 T3 temperature, the critical radius is R3 here. See this. And at T4 temperature here also, you can find the radius will decreasing. That will be R4 here. This is R2, R3, and R4. With the decreasing in temperature, we find the radius of the critical radius of the particle decreases. This it is very difficult to take the class. So many problems today. Okay, we'll continue with this. So, as you find that the critical radius decreases with decreasing in temperatures. So then we are going to the this is all about the homogeneous nucleation, and this is the heterogeneous nucleation, the kinetics associated with the heterogeneous nucleations. So what is that meaning of heterogeneous nucleation? Homogeneous, as we know that homogeneous nucleation means the nucleation of the growth that will be happens in the parent level. Okay, parent phase. So what is that heterogeneous nucleation? The probability of nucleation occurring at certain preferred site is much greater than that at other sites. Heterogeneous means what? The probability of nucleation occurs at certain preferred sites or the preferred regions at which nucleation is much more greater than the other sites. That is unexpected. That heterogeneous nucleation is unexpected. That means in as we said, in homogeneous nucleation, that is for equilibrium. That will distributed, the nucleation is distributed equilibrium to all the sites. But it will heterogeneous nucleation will occur at certain preferred sites, and it is much greater than at other sites. When it will comparing to the other sites, the nucleation will be more. The nucleation rate of nucleation will be more at certain regions. That regions are comes under the heterogeneous nucleations. Example is given here. That is during solidification, inclusion of foreign particles or inoculants, walls of container holding the liquid. During the solidification process, when we go for the solidification, the walls of container, when at the container we are going for the solidification, but the walls of the container holding that liquid, not all the parts of the liquid will not be solidified. That is the example of the heterogeneous nucleation. So what is the factors or what is the energy level associated with the heterogeneous nucleation? That is the solid state transformation, foreign inclusions. Foreign means the other material inclusions or other foreign metal inclusions. Then grain boundaries, interfaces, stacking faults and dislocations, as we have discussed stacking faults and dislocations. So considering force equilibrium during the second phase formation, the equation is that gamma alpha delta equals to gamma alpha beta cos theta plus gamma beta delta. This is the equation how the nucleation will be takes place. If you see, this is nothing but the resolution of the forces, along a particular direction. See, this is the gamma, this is gamma beta delta. If you see what is if you equilibrium, there are generally, if you see the heterogeneous nucleation process, there is the energy levels associated with that gamma alpha delta here, the gamma beta delta is here, and this is gamma alpha beta is here. The surface free energy, gamma is represented as surface free energy. So these are the three-dimensional surface free energy. So if you resolve these forces, resolve these energy levels, that we can find gamma alpha delta equals to gamma beta delta plus cos component of this force, cos component of this energy. So that cos component is gamma alpha beta plus cos theta. This, though the angle is theta, so that means gamma alpha delta will be equals to gamma beta delta plus gamma alpha beta cos theta. That will be the equation. That is the free energy associated for the heterogeneous nucleation processes. So if you see this energy, this equation will be formed accordingly. This so you don't need to go through this details. So we'll go to what is the energy level of this. So we find that del F heterogeneous, that is HET for heterogeneous, this term del F, the free energy at the heterogeneous process is that del F of homogeneous process 2 minus 3 cos theta plus cos q theta by 4. This is the equation. What is that is also the relationship between the heterogeneous and the homogeneous nucleation processes. This is the relationship. Del F heterogeneous equals to the del F homogeneous into 2 minus 3 cos theta plus cos q theta by 4. So when product particles makes only when there is a cos theta term. See, there is a cos theta term. Is theta is 180 degree. What happens to cos theta? If theta is 180 degrees, the cos theta is 0. So whole term, cos theta is 180 degree. If cos theta is 180 degree, the foreign particles do not play any role in the nucleation process. If theta is 180 degree, then the foreign particles don't play any role in nucleation processes. So in that case, the free energy at heterogeneous process is equal to the free energy at the homogeneous level, homogeneous process. See this. If cos theta is equal to 180 degree, that means we put the theta is equal to 180 degree here. We find that del of the free energy of heterogeneous process will be the equals to the free energy at homogeneous process. So that's and then if you see, if the theta is 0 means what? Cos theta. If theta is 0, then cos theta is what? The whole term will be 0. If theta is 0, this term, this whole term, this when the theta is 0, this whole term will be equals to 0. That means the energy level at heterogeneous process will be going to be 0. Del energy at homogeneous process into 0, that will be 0. So that means the term will be here when theta is equal to, this is when theta is equal to 0 degree, theta is equal to 0 degree, and this is when theta is equal to 180 degree. 180 degree means there is no foreign materials inclusion. Okay, there is no foreign materials inclusion. This is, there is no foreign materials inclusion. At that point, we can find out that and the energy level at heterogeneous process will be equals to the energy level at the homogeneous processes. So there is also the intermediate conditions are there. So in intermediate conditions such as where the product particle attains hemispherical shape, if that particle attains the hemispherical shape, then theta tends to 0. Okay, then theta tends to 0. Then we have the formula for this. Okay, del HF is half of the energy level. The free energy level at the heterogeneous process is just the half of the homogeneous energy levels. So there are three. This is the equation. This is the equation for the homogeneous and the heterogeneous energy nucleations. And there are three conditions when theta is 0, theta is 180 degree, and when the product particle attains hemispherical shape. For hemispherical shape, we find this for hemispherical shape. For hemispherical shape, this is the formula. When the shape of the particle will be hemispherical, then the free energy, the heterogeneous free energy equals to the half of the homogeneous free energy levels. So next, there are two terms as we tell that for the phase transformation that occurs due to the nucleation and growth. And we see that nucleation is two categories. One is a homogeneous nucleation and another is the heterogeneous nucleation. The kinetics associated with the homogeneous nucleation process and the heterogeneous nucleation process are discussed. Then now we'll go to the growth kinetics. What are the growth kinetics? So growth kinetic means the after the formation of the nucleus or the nuclei, the growth will occur accordingly with the change in temperature or with the pressure or the compositions. So the growth, how the factors, how the nuclei will be growth, that is the growth kinetics. After the formation of stable nuclei, after the formation of stable nuclei or the nucleus or the nucleation process, growth of its occur until the equilibrium phase is being formed. The growth of the particles will be formed. Growth will be particles will be grow up to what size? Now up to the equilibrium phase is formed. So that means when you are passing through a liquid to solid phase, that means the particles will grow up to all the liquids will be formed to solid phases. That equilibrium phase that will grow until it occurs equilibrium phase. So growth occurs in two methods. That is the thermal activated diffusion. Growth occurs in two methods. The first method is the thermal activated diffusion, control individual atom movement. One process, one method. How the growth will occur? The growth will occur due to the thermal activated diffusion, control individual atom movement. The first thing you have to remember that thermal activated diffusion. Thermal activated diffusion is only for the individual atom movement. This is individual atom movement. The another thing is that a thermal collective movement of atoms. One is the thermal activated diffusion, other is the athermal movement of atoms. First one is more common than the other. So that means this thermal activation diffusion is very much important than the athermal collective movement of atoms. So when you see this, the temperature of nucleation rate, there is the kinetics associated is that temperature dependence of nucleation rate, that is called as U. Kinetics means what? The movement or the movement of the processes, the growth movement. When you're talking about the growth movements, now there is a temperature difference nucleation rate that is called as U. That is called as U. This is the term U. Growth rate I, there is another term, this is called growth rate I, and overall transformation rate dx by dt. These are the factors. See these factors. That is function of both nucleation rate and growth rate. So that is the formula is that dx by dt. That means the overall transformation rate. See this formula. The overall transformation rate is function of both nucleation rate and growth rate. The nucleation rate is U and the growth rate is I. So overall transformation rate dx by dt dx by dt is the overall transformation rate. The overall transformation rate is the function of the nucleation rate u and the I. See, this is the nucleation rate u and the I, as it is written here. Dx by dt, the overall transformation rate is a function of u and I. U is the nucleation rate and I is the growth rate. So if you see this diagram here, this is the temperature difference, temperature with respect to dx by dt. Dx by dt means the overall transformation rate. Here what we find, that will depend on the, see here the black curve is the u means the nucleation rate, I is the growth rate, and dx by dt is the transformation rate. Three terms are along with the temperature del T, change in temperature. See, change in temperature, we find the three values u, dx by dt, and I, as it will form. Okay, and T, what is the T? T is the equilibrium temperature at which the equilibrium phase. This is the at which the equilibrium phase occurs. So this is all. Then we will move to the second, growth kinetics. I'll clear all drawings. Then growth kinetics continued here. The growth kinetics is that the time required for transformation to complete has a reciprocal relationship to the overall transformation rate. There is the time required for a transformation to completion has a reciprocal relationship to overall transformation rate. There is a reciprocal relationship between time and transformation. Reciprocal relationship, or we can say the inverse relationship between the time and the transformation. So the C curve here, this is the C curve. See this is the C curve. So the interesting thing is that started here from that. This is the C curve. Okay, this C curve. C curve means, see here, time temperature transformation. So see this, the time temperature transformation TTT curve. It is one of the most important curve in the material science diagram. I will go through this after the completion of the iron carbon diagram. Still now iron carbon diagram not started. So next, the transformation data are plotted as characteristics S curve. This is a characteristics curve S curve. It is C curve. This is C curve and this is S curve. See the shape of this. Okay. So, at small degree of supercooling, where slow nucleation and rapid growth prevails, relatively coarse particles appear. At the larger degree of supercooling, let me find particles. So there is, this is the when you're talking about the growth of the kinetics or the growth of the nucleations, there are the generally two types of grain structures will be found there. One is your coarse grain and other is the fine grain. So there is the two cases will be there. One is the coarse grain and the fine grain structures will be formed. So this curve is against temperature against change in the log T. Again, this is the fractional transformation against the log T. When you see these two diagrams, this is the S curve and this is the C curve. C curve, in C curve, that will go through the time temperature transformation. That is called as the TTT diagram. This is the most important diagram of the after the iron carbon equilibrium diagram. This TTT diagram is one of the most important diagram in your material science. So we'll go through this in details one by one. So there is no need of the mechanistic growth kinetics now. We'll go through this in TTT diagram. So I think today we have no time again here. Just wait.